In Chapter 22, we introduced the inductor, which is usually just a coil of wire, and the basis of its operation is Faraday's law of electromagnetic induction. We showed that an inductor develops a voltage to oppose a changing current within the inductor. This voltage is given by the following, where delta I over delta T is the rate at which the current is changing, and L is the inductance of the inductor. Because the current in an AC circuit is always changing, an inductor can have a significant effect on the behavior of AC circuits by opposing any changes to currents flowing through them. We can use Faraday's law to show that the RMS voltage across the inductor is given by the following, where X sub L is called the inductive reactance. This is analogous to Ohm's law, where X sub L appears in place of the resistance. The inductive reactance, like the capacitive reactance, is measured in ohms, and it determines how much current exists in the inductor for a given RMS voltage across it. It is found experimentally that the inductive reactance is directly proportional to the frequency and the inductance, as indicated by the following relationship. This relation indicates that the larger the inductance, the larger is the inductive reactance. Note that the inductive reactance is directly proportional to the frequency, whereas the capacitive reactance is inversely proportional to the frequency. The figure shows a graph of the inductive reactance versus frequency for a fixed value of the inductance. As the frequency becomes very large, X sub L also becomes very large. In such a situation, an inductor provides a large opposition to the alternating current. In the limit of zero frequency, i.e. direct current, X sub L becomes zero, indicating that an inductor does not oppose direct current at all. Due to its inductive reactance, an inductor affects the amount of current in the AC circuit. The figure displays graphs of voltage and current versus time for a circuit containing only an inductor. At a maximum or minimum on the current graph, the current does not change much with time, so the voltage generated by the inductor to oppose a change in the current is zero. At the points on the current graph where the current is zero, the graph is at its steepest, and the current has the largest rate of increase or decrease. Correspondingly, the voltage generated by the inductor to oppose a change in the current has the largest positive or negative value. Thus, the current and voltage are not in phase, but are 1/4 of a wave cycle out of phase. If the voltage varies as V0 times sine 2 pi ft, the current fluctuates as I0 sine 2 pi ft minus pi over 2, which is equivalent to minus I0 cosine 2 pi ft. The current reaches its maximum after the voltage does, and it is said that the current in an inductor lags behind the voltage by a phase angle of 90 degrees, or pi over 2 radians. This is in contrast to the purely capacitive circuit we studied in the previous section, in which the current leads the voltage by 90 degrees. In an inductor, the 90-degree phase difference between the current and voltage leads to the same result for average power that it does in a capacitor. An inductor alternately absorbs and releases energy for equal periods of time. Thus, the average power, and hence the average energy used by an inductor in an AC circuit, is zero. As we did with the capacitive AC circuit, we can use phasors to describe the instantaneous voltage and current in a circuit containing only an inductor. The voltage and current phasors remain perpendicular as they rotate because there is a 90-degree phase angle between them. The current phasor lags behind the voltage phasor relative to the direction of rotation, in contrast to that for a capacitor. Once again, the instantaneous values are given by the vertical components of the phasors. There is a common mnemonic that is used to easily remember the current and voltage phase relationships in capacitor and inductor circuits. It is Eli the Iceman, where E represents the EMF or voltage, I is the current, and L and C represent an inductor and capacitor circuit respectively. The word Eli corresponds to an inductor circuit, in which case the current lags the voltage, and the word ice corresponds to a capacitor circuit, in which case the voltage lags the current.